So let's look at an example of a local property. Remember, a local property is a property of a module such that it is true for the module. So let's say our module is called M, and M is an A module. So it is a property that is true for the module M if and only if it is true for all the modules M localized at P. For every prime ideal P, and these prime ideals are of course prime ideals of your ring A. And this is just as a reminder what a local, how a local property is defined. And now for our example, this example is the following. N being 0. This is a local property, and this is what we are going to prove. So what I need to show you, what I need to convince you of, is that it is enough that M localized at P for every prime ideal is 0 to conclude that M is 0. So being 0 locally implies being 0 globally. And if we prove this direction, then of course we have an if and only if statement, because the other direction is trivial. If M is 0, so if M is the 0 module, then of course M localized at every ideal is 0. So there is nothing to prove going from here to here, going from the global scale to the local scale. But in fact, what I'm going to show is using an assumption that looks even weaker at first glance. Namely, it is enough that M localized at M. So big M is your module, and this gets localized at small m, and small m is a maximal ideal. It is enough to have that M localized at small m is 0 for every maximal ideal. This is a weaker statement than saying that the localization at every prime ideal is 0, because every maximal ideal is prime, but not the other way around. But this is enough. So we will show that the assumption that M localized at M for every maximal ideal is 0 is enough to conclude that our module M is 0. So let's look at the proof. This is going to be a proof by contradiction. So we are going to assume that M is not 0. Suppose M is not 0. And we are going to suppose that this condition is true. So M localized at every maximal ideal is 0. And from here we want to reach our contradiction. So if M is unequal to 0, then of course there has to be an element, let's call it X, which is unequal to 0. So X is an element of M which is unequal to 0. And X being unequal to 0 means that the annihilator of X is a proper ideal of your ring A, because after all it cannot be all of A, because for instance if you multiply X by 1, 1 being an element of A, you get X, and X is by assumption not equal to 0, so the annihilator is a proper ideal of A. And now we know that every proper ideal is contained in a maximal ideal. So this ideal, the annihilator, is contained in a maximal ideal. We're going to call this maximal ideal small m. And if we now look at where our x gets mapped to when we project it to m localized at this maximal ideal that contains the annihilator, we see that this gets mapped to this element, x divided by 1. And this has to be 0 because we are assuming that all these modules are 0. So in particular, m localized at m for this m is 0. So x divided by 1 has to be equal to 0 divided by 1. And we can conclude that there has to be a u inside A without m, because remember when we say that we are localizing at m, the subset which is usually called S, we are using to localize is this one, A without m. So there is a u in here such that u times x is 0. So this comes from this equation. Maybe let me explain this in a little bit. Almost fell on my feet here. Let me explain this in a little more detail. So, you have this, and now there is a u such that so this implies there is a u inside here, inside A without m, such that x times 1 minus 1 times 0, which is of course 0, is 0. So we see that what I have already written here on the board. So there is a u such that u times x is 0. But now think about what this means. This means that u is in here. U is in the annihilator. But this is a contradiction because u is not an m, but m contains the annihilator. And this conclusion finishes our proof. So thank you for watching. See you next time.